Velkommen til Forskning til Lunsj fra Institutt for biologiske fag I dag. Så da vil Max
Kreskitelli, ja.
Unnskyld, fortelle om sin forskning på havbruk og kunstig intelligens.
Tusen takk. Okay, I will give it in English. Hello, everybody. Thank you for coming. So I'm going to be talking today about autonomous fish monitoring using artificial intelligence, which is one of the branches that we are developing in the Institute for Biological Sciences here at NTNU. A little bit of my background. I come from the area of robotics. I had experience many years in autonomous systems, in particular in space systems, but now in marine systems as well. And I'm a PhD candidate. I'm working with a joint position between two departments, IHB and IVA. And the title of my PhD is Data-Driven Support for Aquaculture Applications. That is basically decision support systems for aquaculture applications using artificial intelligence. So what do we mean by autonomous monitoring? Why do we want to monitor fish autonomously? And let's take a very famous example about this to put us in a context. I'm pretty sure that most of you know about Tesla Autopilot mode, the self-driving cars. So this is what the car is seeing when they are driving autonomously. It runs neural networks inside the computers of the car, and it's detecting several objects that it has been trained for. And based on those detections, the car is taking decisions completely autonomously. So we would like to reach something like this in under the water with aquaculture. But there are many challenges to overcome. So why would be this interesting in aquaculture? This would allow us to monitor fish 24/7, and we could develop several branches, like understand better the behavior of the fish, stress factors, and estimate the biomass continuously, which also allows to improve the feeding systems and adjusting all the time. Understanding the disease transmissions factors also, because they are interacting all the time with wild fish outside the net pens. And overall, this can help to support a farmer's decisions. But not only in farm fish, we also have a lot of implications in wild fish as well, because the farms have an impact in the ecosystems around them. For example, in the benthos environment, with all the feed that falls from the net pens, they change the benthos, and so the ecosystem that lives in them. Also, we can, if we get farther from the farms, we can also study migration patterns if we are monitoring continuously, see if there are variations, and also we can study the stock, the different species, when do they leave, when do they come, and a big, etc. But there are many challenges to overcome in fish detection autonomously. We have stuff like high gradients in light, for example, which makes it really hard to detect fish in the dark areas. We have occlusion. Also, when cameras get in contact with the seawater, they start developing biofouling, so this needs to be addressed. We have inside the net pens, we have a high density of fish, so this is, I won't say it's impossible, but it's really challenging to perform an analysis of individuals at this point. There's also camouflage. Some species camouflage very well, and these red boxes that I drew here, it's they contain fish inside, but it's almost invisible with a plankton. With all the things under the water. Then we have turbidity, depending on the season and also daily variations. The water might get turbid, and the species might become hard to recognize. And also we have species similarities. This, for example, is salmon, and this is trout. And depending, of course, on the camera systems, the lights and everything, they could look very similar in order to distinguish them. So in order to perform fish detection and object detection in general, we need two things. we need to provide the neural networks images, original images with the objects we want to detect, and also annotations. Annotations are basically information providing the coordinates of the bounding boxes that enclose the object of interest. If we want to detect fish, we have to show the neural network what a fish looks like. And these bounding boxes need to be in a text file that looks something like this, which is disgusting. So each of these boxes will represent each of these boxes, and we would have to do this for thousands and thousands of images. It's not a nice job. So how much data we need, how many images do we need to train a neural network with enough accuracy? And the answer is, it depends. It depends on the complexity of the environment, basically the background and how hard it is to identify the fish. And to have a little bit of intuition about this, let's imagine an experiment. Let's say we want to detect fish, and we show this image to the neural network, and we see this is a fish. And the neural network doesn't know absolutely anything about anything else. Imagine ourselves, like now, for example, if we see a fish, we can classify them, we can associate them with different species belong to fish, which belongs to animals, which belongs to living things, and so on. And we know so much things that it's easy for us to incorporate new information. But if we knew nothing at all, and we just see this image, and we see this is a fish, we could infer that, okay, a fish is maybe this white line here. It could be something dark in a blue space. We could have a lot of possibilities to conclude what really is the fish. We have to basically extract the features that allows us to really guess what the fish looks like. And then if we show more images to the neural network and say, okay, this is a fish as well, this is a fish, this is a fish, we could say, okay, maybe it's not a horizontal line, because here there's also this line inclined and others over there. So maybe a fish is something that is a dark thing with a line in between, and it could be in different orientations. So now we start to extract a little bit more of information, because now we know that it's not just a horizontal line, but something that has a line in any direction. And we start learning more. So this shows you that basically the more information we have, the more data and more variability of the data, the more accurate the system is going to be, because it's gonna learn more. So let's see what happens if we train a neural network, for example, with these types of images that look all of them the same. I mean the same in the sense of the background. We would get something like this. And this is the system running and detecting fish. And it looks pretty decent. I mean, it's getting most of the fish. But the background is the same as before. It's just the water column, doesn't have any complexity. Now, let's see what happens with the same neural network when we add a little bit of background. Then we see that it starts confusing the fish with the chain. And that makes sense, because the only thing that the neural network saw before was a blue background and something on top of it. So we don't know actually what the conclusion of being a fish was. It could have been anything that was on top of a blue water. So it makes sense that it's also getting this stuff. This line actually looks like a saith. If you take the background, this line could be the fish. So this shows us that actually, in order to have an accurate system, we need as much data as possible, but not only the amount of data, also the variability of the data, with as many backgrounds as possible, the rotations of the fish, the positions, because you need to really basically put the neural network in a corner and leave it without any options of guessing. It needs to extract all the possible features that it can to really identify a fish among anything else. A fish or species or anything. This is general for anything else. So the problem we have in aquaculture compared to Tesla, because Tesla is essentially recording 24/7 and getting that data, and it's constantly training their neural networks and learning all the time. So the amount that they have is massive. In aquaculture, we don't have many public data sets with annotations. This is important because you could also use only images for another purpose that doesn't come to the point. But to perform object detection, which is locating the object inside an image, we need annotated data sets. And there are not enough. There are actually very few, and very specific. So we need to work on this a little bit more. And making large data sets, as I showed before, it's not too fun. Even though you need this kind of files, there are tools to simplify this and make it more friendly. This is one tool that is for free on internet, and it's used for drawing the bounding boxes. So essentially, you can draw the bounding boxes around the fish, and the software will translate that to the text file. So you don't need to really write the text file, but you need to draw every bounding box and put the label, in this case fish, or it could be different species, for example. And as you can see, it takes a while. And I'm doing this for one image, 4 fish, but imagine how it is to do it for this. and that for hundreds of thousands of images. It's really not nice. So at this point, we made a question, is it possible that we can automate this in a way that we don't have to really do this process manually all the time? This was the question I got when I started the PhD. Essentially, because when I look at that, I was like, oh no, I don't want to do that. It was too painful. So there is a way to automate this, or at least to support a human. And we can do something like this. If we start with a small data set, even though it's very small, very simple, we can use it to train a neural network and perform predictions. That means detection. When we do those detections, they are not going to be too precise because the data set was small, was not good enough. It's not going to be too precise, but this is going to be something. So if we add those predictions, the good ones, we reincorporate them in the data set, and we retrain. It's like we are teaching the neural network a little bit more and a little bit more and a little bit more. So with the time, it will get smarter, and we will be able to get better predictions and more data, which is essentially one of the things that Tesla does. So, for example, if we run the neural network and we get this image, we can incorporate it directly to the dataset. So I didn't have to draw the bounding boxes. It was just the neural network performing a prediction, put it in the dataset. I didn't have to do anything. So now the dataset starts to grow by itself. So then we have this kind of examples. So here there are two situations. I can either discard that image, I delete it, forget it. So the only thing I would have to go is go through the images, and when I see a wrong one, delete it. Or we can fix this, delete that bounding box only with a tool that I showed before, and incorporate this image and retrain. So now the neural network will see this image without this box and will be like, aha, so this is not a fish. It's just part of the background. And then it will start to learn more and more. So in this way, we can automate the process of creating data sets, or at least almost automate it, because we have to check at the end the result. But it simplifies the task a lot. And it can grow very fast, because imagine a real-time camera running and capturing every frame. So in seconds, we can have tons and thousands of images. The only thing we need to do is to find this starting point here. What is the image data set that we're going to use in the beginning to start? And for that, the idea I had was, okay, ideally it would be nice to have something as complex as possible in backgrounds, with as much variability as possible, so we can have a good start already. And we found this dataset. This is a public dataset developed by Google for training neural networks, and it contains 600 classes of many objects like cars, people, this and that. Fish is one of them, and it contains nearly 7,000 images of fish. So after training a model with these ones, we got a result like this. Really bad. Actually, none of this is fish. A lot of false positive detection. So after taking a look at the dataset, we found that actually the dataset contained all of this kind of stuff. So fish in the form of food, which is fish, but it's not what we really want. Some animals that were not fish, put them over there by mistake, because the dataset of Google is partially made by computers. It's partially made automatically. So those mistakes, it's highly probable that they come from a computer and not because the humans mistaken them. The bounding boxes are also misaligned. Other mistakes are, there are missing bounding boxes. The green ones, I added them myself, but they were not in the original one. And the other type of things is they group elements. So basically, all of this is contaminating the data set, because if we give this to the neural network, it's going to get confused. It's like, okay, what is actually the fish? It's not clear. So I started to clean this data set, and after cleaning it from the almost 7,000 images, I ended up with 4,000 and almost 500 with proper annotations. So after training the neural network with that again, you can see that the result improved a lot. We got rid of all the false positives, essentially. So now we have a good start for use it for us, for starting to create new data sets and starting the path in aquaculture. So now we are ready to create large data sets for ourselves and improve the system accuracy with new images and plan long-term scientific experiments. Because if we now leave a camera running continuously, then that can provide, not only from the engineering point of view of the AI part, but also from the biology or the marine science part, because now we can set long experiments that usually nowadays have to be done manually, either by divers or spending many hours looking at videos. So let's see the potential that we can have with this using streaming cameras. Just as an example, as a use case, I will take these two. They are publicly available. That's why I'm taking them. One comes from the Marine Research Institute in Norway, in Etne Elva in the south, and this one is in Suldalslågen. I will use those two examples. So we start with the model, with the neural networks that I train using the OID dataset, the one that I just showed. And we have the streaming camera running with the system continuously, and this is the kind of things we got in the beginning. So as you can see, it has a lot of false positives. Sometimes it catches fish, but also a lot of trash. So this would be an example, just a snapshot. So what I did was to grab these images. The system is extracting. Every time it detects something, it saves the image. So further on, I can use that image to either to use it for science or to just incorporate it for training the neural networks. So I took this kind of images and I fixed the mistakes. For example, I deleted this big box and I left the other ones because those were correct. And I incorporated them back to the data set and retrained the neural network. So basically what I'm telling the neural network is all the information that you knew before about fish, now add this as well. So now I ended up with from the images that I extracted in the beginning, I took 734, fixed them, retrained the data set, exposed the neural network to these new images, and this is the result afterwards. So you can see we got rid of all the false positives, and now it's working really nice. And you might say, yeah, actually that's worked very nice for this fixed camera in this place, and that is true. And this is because we have too little images. What I did before was training with 4,000. We are talking about 4,000 hundreds. And for these systems to run properly, you need hundreds of thousands if you want them to be dynamic in many environments. So the idea I got at this point is, okay, now I could do all of this in one day. Let's say 2 days if we leave the system running and go to sleep and see it the next day. 1 day for capturing images, the next day for fix some of them, retrain the system, and leave it running. So in 2 days, basically, we can have a streaming camera running beautifully. So also, we can think of having multiple streaming cameras, not only just one side, but we can have many, deploy several cameras and have them running at different sites. And you can see, for example, we have here, in this one, sadly enough, I didn't have any fish. But luckily, we didn't get any false positives either, which is good. Here, there is a fish a little bit hidden. You can see the resolution is very low, and the water is a little bit turbid. So I wasn't even expecting to detect this one. I was a bit happy. But the thing is that by doing this, we can start storing those data. You can see here, every frame, here I'm detecting at 1 frame per second. Every frame, every detection, I'm saving it. And then I can correct these images and incorporate them to the data set and retrain again. So we can think of, now the possibilities get really endless, because we can set up cameras in different places, adjust them for those places specifically to run properly, and then we can start getting a lot of data. And with this, we can either use them for those places if we only care about that, but we also can gather all this, and we can really start creating very large data sets, which ultimately can be used for training accurate systems and make them more dynamic to different environments, because then we can put this in an AUV, for example, and navigate. And now if the environment starts changing, we can start thinking about Tesla now. If we are changing the environment, we have seen so many environments now that we have a very accurate idea of what the fish looks like. And I've been talking about fish in general, but we can also think about species. So we can, for example, we can train the system to recognize different species, and, for example, a category that is, okay, this is our unknown species. So we could, for example, every time a new species appear, we categorize this in an unknown species, and then we can label it by a human, incorporate them to the data set, and okay, we get a new species in the system that can be recognized, and so on. So this can start growing really, really much and scale a lot. So at this point, we have to basically take a path here. I mean, in the institute, but we can do a lot of work from the engineering point of view. If you want, from the technology side, we can start putting streaming cameras in different points of interest and centralizing the information, gathering a lot of data, and also publishing it, because there are a few companies working on these topics, but none of them releases anything. And this is why, when you look at the literature, basically all the scientists are working with a few public data sets, and everyone is quite stuck because there's nothing. There's not much more to do because there's no more data. And in AI, everything is data. You have, of course, the methods, which are good. They are quite developed already and quite advanced. But as you have seen through the presentation, depending on the data you use, it will change completely the accuracy. So it is important also to make this data available for the scientific community in order to start pushing the boundaries, because the topic is quite stuck when you compare it with other applications, such as the driving, such as in China, for example, they are doing surveillance with people now. They are actually identifying people in the streets with the cameras. And this is because those data sets are massive, and they're, so it is easier to get more accurate systems. So this is it for today. I left 5 minutes for questions because I wasn't sure. Thank you. I don't know if there are any questions or.
Is it possible at this time to, like in China, they recognize the individuals at fish level? Is it possible?
There are companies actually talking about that. It's really, really challenging because, for example, the salmon, this is a topic I'm not an expert in. It has to do more, maybe some biologist can correct me. But for example, I know that the salmon has something like, or footprint with the pattern that they have in the body. So you could, in theory, identify every individual with that. Doing that at this point would be extremely challenging because essentially the challenge that you have is the wilderness. If you just put a fixed camera inside the farm, it's hard to get a really good image. So the devices some companies are working on is to try to make the fish pass through a tube or somewhere where you can have it close and have a real good image. In that case, I think it would be possible. There are still a lot of challenges, but I see it way more possible than in the wilderness, or I mean, in unbounded environment. Can you repeat? Hmm. If it happens, if it's happy. Oh, yeah, yeah. Essentially, you can detect anything that you train the neural network for. The only thing you need is the data. For example, if I want to see the difference between a healthy fish or a dead fish, then I need images of both, and then I could detect for that. Another thing, for example, that is interesting is to detect the deformed fish. I've seen several of those inside the net pens. The farm fish, some of them are with deformations in the body, so you could also identify those. For example, that wouldn't be so hard to do at this point. We just have to take a lot of video, and whenever we see one with deformations, we get those images and train the neural network, and that can be done straight away. We only need the video we only need to catch the bad fish there, but it can be done. Yeah. It can be done at both levels. Again, the only thing we need is the data to train it for. Sometimes the data you can just catch it naturally, or you can force it. You can actually take that fish, try to do it outside the water, for example, or even force it. I don't know, with a dead fish, you could try to provoke some injuries, anything. The only thing is, think of it when you think of which kind of things can you detect. Essentially, anything that the camera sees, because after that you just need to get a good bunch of images, show it to the neural network, and then it will be like, aha, so this is sick fish, this is that kind of thing. As long as it is visually, you can see it visually, it can be done. And of course, ultimately, you are also bounded by the quality of the camera systems. If you want something super detailed, you need to be able to catch it with a camera. Otherwise, in the water, we have that challenge, the turbidity. Sometimes maybe you have a beautiful image, super clear with the water, and sometimes all the patterns are gone because it's super turbid, especially in the spring when everything sprouts. And
Fler spørsmål da? Just want to say thank you, Max, for this very
thank you.
interesting, and I think we've learned a lot, and
I hope.
not to mention we've learned how much work it takes to do proper research. I'm sure this can be transferred to many other areas.
Yes, actually, yes.
So
Thank you. Oh,
presentation.
thank you.
Start on the cafeteria.
Okay, thank you very much. Thank you for coming.
Ville bare legge til da, at de som er interessert i havet, så er det et spennende arrangement i morgen klokka 6 på Parken kulturhus, som også handler om hav og miljø da. Så da kan man drikke vin og mingle litt, og det blir en hyggelig kveld. Så velkommen dit.